Simulating stiff materials is a challenging and critical problem across fields. Here, rigid body methods have long offered efficient solutions. Widely available libraries, exemplified by Bullet, have made rigid body simulation accessible and provide fast and scalable results. But in order to achieve this performance, underlying algorithms in these methods cannot provide guarantees. This means that as scene parameters change and contact complexity grows, significant intersections, instabilities, and even outright failures can happen. Recently, researchers proposed rigid IPC, which guarantees robust, accurately solved, intersection-free rigid body simulation. However, to achieve these guarantees and strictly keep bodies from interpenetration, rigid IPC requires continuous collision detection on rotational trajectories. Rotational CCD is very expensive, and so makes rigid IPC much slower than currently available fast solvers like Bullet. To obtain the best of both worlds, we propose Affine body dynamics, or ABD. ABD simulates stiff, close to rigid, frictional contact dynamics with both guarantees of non-intersection and speeds that are comparable and faster than highly optimized rigid body libraries like Bullet. While rigid IPC and other traditional rigid body methods treat stiff materials by enforcing rigid motion, ABD instead applies compact, affine coordinates with a stiff rigidity potential. When combined with barrier potentials for contact handling, this choice ensures that trajectories are piecewise-linear, and so allows ABD to employ efficient and robust linear CCD methods to ensure non-intersection. In turn, this gives ABD on average a 3-order magnitude speedup when compared to rigid IPC, and an up to 8 times speedup when compared to fast rigid body solvers like Bullet. At the same time, ABD maintains stable and intersection-free trajectories at all time step sizes. Let's begin with the side-by-side comparison between ABD and rigid IPC. Here, smashing a wrecking ball into blocks, ABD achieves a more than 100 times speed up over rigid IPC with comparable, high-quality results. ABD likewise accurately captures frictional contact. Here, ABD correctly captures the stable behavior of a masonry arch with an over 70 times speed up. Since ABD is based on a stiffness model for its constitutive behavior, we can also apply ABD to simulate stiff elastic responses. For example, the stiff ABD card house on the right can lightly oscillate while still accurately modeling friction to correctly capture stability. Here, ABD provides a more than 100 times faster drawn time when compared to rigid IPC. To study the scalability of ABD, we start with the 8x8 chain net example. On the left, we again have the rigid IPC results, while on the right, ABD comparably models the shock in the drop chain links with the interpenetration-free contacts. Here we see a 30 times faster performance for ABD on this small-scale example. Next, we increase the chain net to 16x16, and also further increase the simulation complexity by dropping a heavy falling sphere onto it. Here, ABD now outperforms rigid IPC by 600 times speed up while continuing to provide intersection-free trajectories. As we continue to grow the scale of the domain, here at a 96x96 chain net, we're well past what is possible for both the rigid IPC and Bullet solvers. With a domain this large, the chainmail net rebounds with the initial waves clearly propagating along. ABD's combined scalability and robustness can be pushed to the extreme. In this challenging stress test example, we simulate a complex 28-gear system with frictional contact resolving all interactions. Here, the surface meshes contain well 2.5 million triangles with over a quarter in contact at every time step. ABD is able to simulate this model at 11 seconds per time step, with large time step sizes, while on the GPU, we've successfully accelerated it further by 85 times. With the torque applied to this actuated gear driving the motion, we're able to directly visualize the magnitudes and locations of contact forces. This again highlights the challenge of this example, which confirm cannot be simulated by either rigid IPC nor bullet. Next, let's consider a side-by-side comparison between ABD and bullet. For a bullet comparison, we start with a modified version of the wrecking ball. Bullet best supports convex-to-convex body contacts, so we've eliminated the chain geometry to give bullet a better advantage. Here we see that a moderated time step in these examples, bullet generates large intersections. They need to be reduced to at least 1 millisecond to reduce the worst of them. On the other hand, ABD remains intersection-free for all time step sizes, obtaining responsive dynamics. For the smallest example, we see that ABD and bullet have comparable timings, but as we scale to the larger things, ABD begins to outperform bullet with up to 8 times speedup. For non-convex bodies, bullet and most other rigid body libraries require replacing input surface meshes with pre-made proxies built from convex components. This requires slow handcrafting or hand-tuning of parameters in convex decomposition codes to get reasonable proxies. Even with the best proxies, many critical details are often lost, resulting in inaccurate simulations as we see here on the left. Here, with the bullet proxies, the detailed geometry of the intricate dragon skeleton is incorrectly bouncing off the sharp needle tips. On the right, ABD directly simulates on the input triangle meshes, resulting in accurately modeling detailed loops in the skeleton being caught on the tips. Because of its linear coordinates and incremental potential contact model, ABD also seamlessly and directly couples with deformable finite element domains to create hybrid finite element affine models that efficiently simulate heterogeneous materials. Here, the main body of the ship and helicopter are modeled with stiff ABD, while the cabins, rotors, and wheels are all simulated with soft finite elements. Thanks.